Okay, so here I have got a very interesting activity for you, and this is not an activity actually. This is just an observation that I've made, and I am pretty sure that you might have also observed this. Okay, so here I have a door, and I am pretty sure you guys might also have a door at your home. So what you and I think you should try this at your home yourself also. So just take a door and try opening the door or closing. Here I'm opening the door. So try opening the door by applying a force at this point. Okay. So what I do is I apply a force here. Okay. So before that, this is a door, and this part of the door is called the hinge. Okay, the hinges. Okay. This is the part that attaches the door to the door frame, and this is also the axis of rotation. So the door is rotating, right, and it is rotating around a fixed line. This line. Okay, it is rotating around this. So this fixed line is called the axis of rotation. Now, I am so first of all try this out at your home yourself. Apply a force um, uh, at a point near the axis of rotation. So let's say I'm applying a force here. So I try and open the door, and it takes quite a lot of effort to open the door, actually. And then try the same thing by applying a force at this point near the edge of the door, away from the axis of rotation. And now if I apply some force, it is pretty easy for me to open the door. So that is an observation that you guys also might have noted. Okay. So yeah. Okay. Let's try one other thing. I'll try to apply the same force at two different points, and let's see the result, the outcome. Okay. So here I'm applying some amount of force at this point, at the edge of the door. Okay. And as you can see, the door opened quite quickly. Okay. Now I'll try to apply the same force at this point, okay, close to the axis of rotation, and you can see the door is open quite slowly. So now let us pause for a moment and think about this. What's happening here? Here, applying the same force at two different points gives us two different results, which is not generally observed in other physical phenomena. Okay, so I think we should look at this from the point of view of physics, and to do that, we first need to make a diagram. So yeah, let's go and make a diagram for this. And in our diagram, we'll be looking at the door from the top view. So we'll make a diagram from the top view. Okay, we'll be looking at the door from the top. So let's make the diagram. Okay, so here I am with my diagram, and if you can look, this is the top view of the door. So this is my door, and this is the hinge. Okay, so this is the part, this is actually the door frame. Okay, and this is the part where the door is attached to the uh, door frame. Okay, and similarly I have made another diagram to show the second case also. Now here I am applying the two forces. So these are the force vectors. This is the force in this case, and this is the force in that case. And because both the forces are equal, I have made arrows of equal lengths. Okay, so the only thing that is varying in both of them is this length. So let this be L1. Okay, this length, the length or the distance between this force, the point at which the force is being applied, and the axis of rotation. So let this be YL. Let's call it distance. So because this is distance, let's call it D. So D1, and in this case it will be D2. This distance D2. So only the distance is different. The force applied in both the cases is the same. Now we'll have, okay, so now because we are getting different outcomes in both the two cases, there has to be a second thing or a second variable, okay, which is responsible for the effect that is being produced. So it is not the force that is producing the effect, because if it was the force, then because the force being equal in both the cases, we would have got equal results. But because we are not getting equal results, this door is opening faster as compared to this. Therefore, there is a second variable, and we can call that, let's say, door opening force. Okay, for now. Why? Okay, and this is the rotational analog of force. Why rotational analog? Because this kind of a phenomena is only observed when we have rotating objects. So here we had the door rotating around the axis of rotation, and this same phenomena can be observed in other things, other rotating objects. Okay, so that's why we call it this second thing that we are talking about, the thing that is responsible for the result. Okay, so the door opening force, whatever you call that, whatever you want to call it, so that is the rotational analog of force. So now let us analyze the thing in a much more mathematical way. Okay, so let us notice door opening force with some letter. And generally physicists use the Greek symbol. I don't know if it's Greek or not. This symbol, okay, this is called tau, T-A-U. So this is just a symbol, okay. You can write A, B, C, anything else for it, but because this is being used, so I'll also stick to it. So we'll use tau to denote that door opening force. Okay, so this is the door opening force. I'm not writing door opening force because that's too long. So tau. So door opening force, which is tau, equals or rather let's start by writing what it is proportional to. So this is obviously proportional to the force applied. Why? Because if I apply a large amount of force, my door will open much more quickly. Okay, so obviously it is proportional to the force. If I had applied a larger amount of force here and here, both the places, my door would have opened much faster. Okay, so it is proportional to the force clearly. Also, as you can see here, it is also proportional to the distance. Here the distance was this distance. Okay, this distance was large, so I had a larger door. I had a larger tau, the door opening force. In this case, my d1 was smaller, the distance was smaller, so I was getting a smaller door opening force. Okay, so obviously this is also, tau is also proportional to this d. Here it is d1, here is d2, so generally d. Okay, and there's a third thing that it is proportional to, which I'll just show you right now. Okay, so I think I have to go to the door and show it to you there. Okay, so let's go there. Okay, so here I am again next to my door, and I am trying to demonstrate something here. So here I'm going to show you the third variable on which the door opening force depends. I'm sorry if there's a noise in the background because I have pretty annoying neighbors, so please ignore them. Yeah, there you see. So here I have my door, and earlier I was so in all the previous cases I was applying a force perpendicular to the door. So this is the door. Okay, so I'm applying a force perpendicular to the door always. Okay, in all the cases, but it is not necessary that I apply the force always perpendicular. I can also apply it at an angle like this, or simultaneous angle, maybe this. So I could apply the force like this, or maybe this, or at any angle. Okay, okay. So even the door opening force also depends on this angle. So you could just try it out. Okay, and from our general experience, whenever we apply a force perpendicular to the door, it is easiest for us to open the door. See, I can very easily open the door here, but if I apply a force at an angle, let's say this, it gets a bit it's not that easy to open the door. Okay, and we'll come to that in a while. So you can just try it out. Okay, so I'm talking about this angle, the angle between my finger, this finger, and the door. So this is one, so this is the door and my finger, so the angle between these two. So I'll just show you that in the diagram in a second, but just try it out for yourself. If I apply a force at such an angle, this is a very awkward angle to open the door. Nobody opens the door like that. Okay, nobody opens the door at this angle, but if I try it, it'll take more force to open the door. Okay, so now let's go back to the diagram and just add in this variable also. Okay, so we just saw that this door opening force, so to speak, is also dependent on the angle at which you apply the force. So here this angle is what I'm talking about. So in this case this angle is 90, but this angle in other cases might also change, right? I might apply a force at this angle, so the angle might reduce. Okay, so let us denote this angle by theta. Okay, so okay, and it also depends on this angle. Now how exactly does it depend on the angle? The door opening force, okay, is not exactly directly proportional to theta. And why so, we'll just see in a moment. Let's say okay, for a moment, in this case, I don't apply a force perpendicularly, okay, directly. I am not applying a force perpendicularly, but at an angle, okay. Let's say I apply a force at this angle, or maybe this angle, okay. I'm applying a force at this angle, okay. Okay, so this is theta in this case. Now, using your early knowledge of vectors, you might resolve this force vector into two components. First, this component and this component. Okay. Now here, if you see clearly, this theta in this triangle, this component is your sine component. Okay. Why sine component? Because in this triangle, this is the perpendicular, right, of this triangle, opposite to the angle. Therefore, this is your sine component, sine theta component, and this component is your cos theta component. Now, if you look closely, this component is pointing okay, along the door. And if you have ever tried applying a force along the door, it does nothing to the door, right? For example, if this is my door, okay, if this is my door, if I pull the door in that direction, the door would just not move. Why? Because it is fixed at this point. It'll not move. So this cos component is just of no use. It'll be cancelled out, okay, by the force applied by the hinges. Okay, so this in no way contributes to the door opening force. Okay, but what contributes is only the sine component of the force. So this tau is also not equal. Sorry, is also proportional to sine theta. And that's it. I believe these are the three things on which our door opening force depends. Now, earlier physicists have dealt with this, and they've given a specific name for this so-called door opening force. So now onwards, we won't call this door opening force. There's a new name for this, which is torque. I'll just write it TORQUE. And you might have heard this word in respect when you've heard this, you might have heard this name when people might be talking about cars or something like that. Okay, torque. Okay, so the engine provides this much torque and so on. Okay, so but we'll come to that later. Okay, here torque is the door opening force that we were talking about. Okay, so this is the name given by physicists to the door opening force, so we'll call it torque now. So torque, which is denoted by tau. Okay, yeah, and it depends on these three things. Now we might combine these three things into one equation, and there you go. Tau equals F into D into sine theta. Now, some of you might have the question that why don't we have a proportionality constant here? Like we have in other cases, like we have in other cases we put in a k, right? When we remove the proportionality sign, we always introduce a proportionality constant. But in this case, we don't have a proportionality constant. Why so? Well, it is so because in this case the proportionality constant is simply 1, and it actually doesn't really matter if our proportionality constant is 1 or 2. Why so? Because this tau is actually, there exists no such thing as torque. This is only there to compare two situations. In this case, you have more torque. So in this case, you have more torque. In this case, you have less torque. There is no actual physical significance of torque. It is just used to compare two situations. Okay. So in this case, where we apply a force away from the center of rotation, axis of rotation, we get more torque. So that's why we don't have a proportionality constant. Okay. And even if you don't fully understand why we don't have a proportionality constant, don't worry. It's not very important. All you need to understand at this point is torque equals F into D into sine theta. And here, this is a vector, this is a vector, and yeah. And now you have to think, is this thing a vector or not? Torque. Is it a vector? So I think we should end the video at this point. Okay. And just give it a thought. Is torque a vector or not? It has a magnitude, of course. We'll get some magnitude, but does torque have a direction? Think about it, and I'll talk about it in the next video. Okay, till then.